Okay, hello everyone. So in this session we are basically trying to introduce three very important abstract structures of mathematics, which are so-called groups, rings and fields. So let me just name them first. So what we are going to study is the notion of groups, rings and fields. Okay, fine. Now these three, as I said, are quite abstract structures in the sense that when you will be first introduced to these notions, it's quite a bit difficult to visualize them out. For example, if you are already introduced to real analysis, there is a way to visualize things of what's happening, right? For example, how a sequence converges, what does it geometrically look like? But you absolutely cannot attach a geometrical notion to these abstract structures. And in some sense, you need to study them for the sake of themselves. But slowly, if you start getting involved in these structures, you will eventually come to notice that these are essentially very useful in solving complex mathematical functions. For example, if you get very much involved in studying the fields, the structures of fields, you will get to know that they are of extreme importance when you are involved in studying polynomials. Right? Now, more or less you are already introduced to what polynomials look like when you were in schools, and I guess you are already introduced to how polynomials work, and the notions of reducibility or irreducibility, in very simple sense what roots of polynomials typically are, those sort of things are of extreme use in mathematics. And to get involved in such structures, you need to get hold of the notion of fields. But you cannot get hold of the notion of fields just like that. For that, you need to build up the fields step by step, and the first basic structure to get hold of what a field basically is to get hold of the notion of a group, right? And sort of all these structures are being developed, kept in mind the most useful number system which you have already studied, which is the natural number system, or specifically the integer system, right? Now you know, for example, that like this is the notation for the integers, right? So this is how you denote this set of all integers. Now as you know that if I choose any two integers, any two arbitrary integers, say a and b are two integers, then we know that if I add them, I'll still get an integer, right? I'll still get an integer. Essentially, if I subtract them out, I'll also get an integer. Now we also know that there is a very special element in the collection of integers, which is the number 0. And why is it so special? Because if you add anything to 0, you will get back that number itself, right? For example, if you start with 2 and you add it to 0, you will get back 2. That's very lame, fine. Moreover, when you are studying with integers, any number you choose, any integer you choose, and specifically for every integer you choose, you will always get an element which, if you add to the element you started with, you will get 0. For example, if you start with 2 and you add to it the integer minus 2, you will get back to the element 0, right? So these are some axioms which are specifically used to develop the notion of groups. So you can think of groups as sort of a generalization of whatever is happening in case of integers for an arbitrary set, right? There are multiple such motivational examples which are actually used in order to construct out groups, but those sort of are not that introductory as the collection of integers is. For example, you could have also served the example of reals, complexes, rationals as a motivational example for studying groups, because all these, with respect to our usual addition, will serve us the example of a group. Because whenever you take any two numbers from this set, if you add them up, they will still be in this set, right? For example, if you choose two real numbers, you add them, you will still get a real number. If you choose any real number and add it to the element 0, you will get back that very real number. And for every real number, there is an element which is specifically the negative of itself, which when added, you will get back the element 0, right? So this sort of helps us in constructing the notion of groups. So let us get to the basic definition of group. So the definition of a group. Okay. So let G be a non-empty set, right? Because if we are concerned about talking about elements from it, I need it to be non-empty. So let G be a non-empty set, and let star be any operation. What do I mean by operation? Now there is a very sort of a very rigorous definition to what an operation is. Specifically what we mean is not just an operation but a binary operation. Be any binary operation. So the more rigorous formulation of what a binary operation is that it's basically a function from the set cross itself to the set, and it will took any two elements, suppose A and B, and symbolically it will map it to the element A star B, and that element should also be an element of G, right? To keep it very simple, you can just think of star as our simple addition, or rather how we use the notion of addition. Okay, when we develop the theory of groups, we use the conventional symbol for multiplication in order to in order for the operation to be sort of relative to the student, but the basic formulation is of this form, right? So star is any binary operation. By binary operation we mean a function which is of this form, which obeys the following axioms. Okay, what are they? Number one, okay, the operation needs to be closed, right? That is, for all elements A and B coming from this non-empty set, if I operate them under this operation, I'll get back an element from G itself, right? But this property is already been taken care of by the word binary operation. So a very simple definition of binary operation, as I have already stated here, it seemingly takes care of the fact that whenever I choose two elements, I operate them using this operation, I'll get back an element. So this is technically not required under the axioms. The next axiom which is required is the notion of associativity. That is, whenever you choose two elements from this non-empty set, three elements rather, so let A, B and C be three elements from G, then in which order you operate them is not something to be concerned about. That is, if you operate B and C first and then operate with A, is same as operating A and B first and then operating with C, right? As we know, in case of integers, this is exactly equal to first adding 2 and 3 and then adding it with 5. Clear? Fine. Number 3 is the existence of identity element. Fine. So what do we mean by the existence of identity element? That means there exists an element which we denote as E in G, such that for every element A in G, if I operate E with A from either side, I'll get back A. Fine. And if I operate E from the left as well, I'll still get back A. Fine. For example, as we talked about the element 0 in the case of integers. So if you choose any element and you add it to 0, you will get back that element, and it doesn't matter from which direction you operate it out. Fine. Okay. The next axiom which is required is the existence of inverse. The existence of inverse. Fine. So what do we mean by this? That is, for every element A in G, there exists an element B in G such that if you operate A and B from any side, you will get back the element, we have used the notation of E, right? So we will get back the element E. Fine. So, and this should be equals to B star A as well. For example, if you talk about the element 2, then adding it with minus 2 will get you back 0, and it is same as minus 2 being added from the left. Fine. And a fifth property, which is technically an optional property, is the notion of commutativity, that is changing the order of the elements being operated. That is, for all elements A and B in G, operating A with B is same as operating B with A. Fine. Okay. So if you have a non-empty set with an operation defined on it, and that set follows the first 4 axioms, then we call that set along with that operation to be a group. Fine. Moreover, if it in addition satisfies the fifth property as well, then we say this to be an abelian group. Fine. Getting hold of it? And already we have been motivated by an example, but let us rigorously work out another example as well. Okay. Now, the definition of the operation is up to you in some sense, because if you are given a set and you need to check whether it forms a group or not, the first thing you need to get hold of is whether there exists an operation or not which satisfies these axioms. Okay. So, example. So, we claim that the real numbers with respect to addition is a group. Fine. So, let us try and prove it out. Proof. Right. Number 1, we already know that if R1 and R2 are 2 real numbers, then R1 plus R2 is also a real number, and that comes from the basic properties of real numbers, right? The second property is that if R1, R2 and R3 are 3 real numbers, then again adding them in combining any 2 of them is the same, right? And these 2 holds from the basic properties of real numbers. So, these 2 axioms are nothing to be concerned about. Number 3 is that observe that for all elements, for all real numbers R, if you add it to 0, you will get back the number itself. Fine, from any side you want to add. And number 4 is that for every element, every real R added to minus R will basically give you 0. Fine. And we know also the element minus R will also be a real number once R is a real number. Fine. Therefore, it is a group, right? Therefore, R with respect to addition is a group. Fine. But something more can be checked, that we know that the addition is commutative, right? Addition is commutative. I can add 2 elements from any direction. Fine. So, addition is commutative, which implies that R with respect to addition is an abelian group. Is an abelian group. Fine. So, this is the best introductory example one might come in hand when you are getting an introductory course on group theory. But there are many such examples which actually tell you the fact that groups need not be abelian, right? And I do not need to I am not concerned about those examples at this point, because this is sort of a lecture which deals with all the 3 basic algebraic structures which you need to learn. So, let us get on with the other algebraic structure, which is the notion of a ring. Fine. Now, what a ring is. So, what is the motivation behind introducing the notion of ring? And once you understand the motivation, it is completely clear. So, suppose you are given an additive abelian group, okay? An additive abelian group. What do we mean by an additive abelian group? So, by an additive abelian group, what we typically mean is that we have a group G and the binary operation is addition. Okay, so this is addition, and the group is abelian, that is commutativity holds, and the group is abelian. So, whenever you are given an additive abelian group, the first example which should click your mind is the integers. Fine. Okay, right. Fine. Now you are given an additive abelian group. What I want to do is I need to add one more mathematical structure to it, such that it sort of enriches this collection. Okay. Now we know that there is another important mathematical structure which can be introduced to the collection of all integers, which is multiplication, right. That is, if you choose any two integers, for example 2 and 3, if you multiply them, you will still get back an integer itself. Fine, any integer will do. Therefore, this actually, sort of suggests us that given an additive abelian group, we can try and attach another binary operation to it. Okay. So the definition, let G with respect to addition be an additive abelian group. And in a very simple sense, we actually do not need the notion of it being an additive abelian group. It suffices for it to be just be an abelian group. So let me just give the general definition. So let it be an abelian group. Okay. Let dot be a binary operation, on G such that this operation is associative. That is, if you choose 3 elements from this group, then A times B times C is same as A times B times C. Fine. In that case, we say that the group which we already started with, along with this third operation, forms a ring. Fine. So this is sort of a triplet, right? I have a set and I have two binary operations. Okay. And the only non-trivial axiom which we require for the third operation is being associative. Fine. That suffices us to form a ring, which we can easily understand when we are studying about integers, right? That is, we know that in integers multiplication is associative in nature. Getting my point? But then now there is a very important fact about multiplication. Like we know that when we had introduced the notion of a group, there we did not have any specific criteria for what the operation must be, right? So the operation can surely be multiplication, right? Now the thing is that, suppose, let us again study by an example. So suppose we consider the example of Z. Fine. Now we know that already Z with respect to addition is an abelian group. It's an abelian group. Fine. Now we have the usual multiplication for the integers, right? Now observe that Z with respect to multiplication is not immediately a group. In fact, what is more specifically required here is that it's not a group. Okay, let me first check that whether it's not a group, right? So it's not a group. Why is it not a group? And the checking is very obvious, because for it to be a group, we need to get hold of an identity element, and we know that the identity element, when we are talking about our usual multiplication, is the element 1, right? If you multiply any element to 1, you will get back that element, and if you multiply any element to its reciprocal, you will get back 1, and this is the criteria for the existence of identity, existence of inverse, right? But you can easily observe that in case of the integers, any element other than 1 and minus 1 does not possess an inverse, right? Because the inverse of 2 under usual multiplication should be 1 by 2, but 1 by 2 is not an integer, right? So the collection of integers, it does not immediately form a group because it does not possess an inverse. But one thing which can be checked immediately, that it does have an identity element, right? The existence of identity is guaranteed. the existence of identity is guaranteed, which is just 1, the number 1. Fine. But what is the next problem which arises here? The problem which arises here is that if you multiply 0 with 1, since 1 is the multiplicative identity and 0 is an integer, you need to get back the element 0, which you are surely getting. Fine. Got it? But let us get to the element, to the group of the reals, for example, under multiplication. Now you can observe that now it is no more a problem for the existence of inverse of any arbitrary element, right? But there is a problem here. So what I mean to say is that this is a group, and you can check it as an exercise that real numbers with respect to usual multiplication, this does form a group. But what is the problem here is that, observe that so let me just clarify step by step. We already have associativity. Closure is already defined in terms of it being the usual multiplication. The existence of inverse is also guaranteed. Existence of identity is also guaranteed. Identity is guaranteed, right, which is the element 1. But the problem arises in the existence of inverse. Why is it so? Now if you choose any arbitrary real number which is a non-zero real number, you will get hold of an inverse immediately. For example, if you choose the element 2, 1 by 2 is surely a real number, and it will give you 1. For example, if you choose the element root 2, 1 by root 2 is also a real number, and it will give you the element 1. But 0 has no inverse under multiplication. Because whichever number you multiply to 0, you will never get 1, right? For the inverse to appear for 0, I need to get hold of such a number which when multiplied to 0 will give you 1, but there exists no such number which when multiplied to 0 will give you 1, right? Fine. So what is the possibility to make the reals a group under multiplication? So the only possibility is just to remove the element 0 and consider the collection of all non-zero real numbers, and then it causes no more problem. So what we typically conclude from here is that the real numbers except the element 0 with respect to multiplication is a group. In fact, an abelian group. Right? Now let's get back to our definition of rings. Okay. So how we have defined rings, if you just recall. So our definition of ring was, so we need to get hold of an abelian group, and I need to get hold of a third operation which is which we call to be multiplication, and the multiplication operation must satisfy only two axioms. One, that the set is closed under multiplication, that is whenever two elements are operated under multiplication, you get back an element from the set itself, and the operation is associative. Fine. If G plus dot is a ring, right? So we have defined groups. Using groups, we have developed the structure of a ring. Now you are given a ring, and G except the 0 element. What do I mean by the 0 element? So that is the notation for the additive identity. That is the identity of the structure being considered as a additive group. Okay, or G with respect to plus. Now see, whenever you will be studying algebraic structures, the usual notations of the operations will be plus or dot, right? And it is a convention that whenever we are studying rings, the operation under which G is assumed already to be an abelian group is conventionally taken to be addition. So we always use the term additive group, the additive part of the ring. That means that we are just concerned about this group structure G with respect to plus. It can be any arbitrary operation, but that is something which we are not concerned about right now. Fine, right? So you can think of this the additive identity, or if you are getting too much confused, so 0 is the notation for the identity of the first operation, which we have denoted as plus. Fine. Okay. In case of arbitrary structures, plus directly doesn't mean your usual addition, dot directly doesn't mean your usual multiplication, but they are just they are merely symbols for depicting certain operations. But moreover, the uses are usual additions or multiplication, depending on the set which we are concerned about. Fine, let us not get into too much of confusion. So, but 0 is the additive identity. So, what we are trying to do is that we are picking up the group structure of the ring with respect to the first operation. It surely has an identity which is 0, or by our usual notation which we have started previously, E, we remove that element, right? We remove that element, and the rest of the structure which is left, which is G minus E, the set G minus E, if this set with respect to the third operation, or rather the second operation which we have depicted to be multiplication, if this forms a group again, rather an abelian group again, then we call this triplet to be a field. Okay. So, formally a ring G plus dot is said to be a field if G except 0 with respect to the operation dot or the multiplication is an abelian group. Fine, where 0 depicts the identity with respect to the first operation. Fine. Okay. So, we have studied the structure of groups, we have introduced the notion of rings, and also we have introduced the notion of fields. Okay. And one thing you need to be careful about, that is, whenever you are studying these topics, these algebraic structures, plus and dot, they are merely symbols depicting operations with respect to the set. For example, if you are given this set to be integers, then we know that this addition will obviously mean your usual addition, multiplication will obviously mean your usual multiplication, be it Z, be it Q, be it R, be it C. Fine. If you know what matrices are, then in that case multiplication and addition are slightly makes different senses, but they are again usual with respect to the set we are concerned about rather. So, this concludes this session. Meet you guys soon in some other session.